Hello everyone. So in this video I'm going to look at just two problems from chapter 36, problems 14 and 69. So this will be from the first part, the first 7 or 8 sections of the relativity chapter. Alright, so in problem 14 we have an unstable particle that's produced in an accelerated experiment which travels at constant velocity covering 1 meters in 3.40 nanoseconds in the lab frame before changing into other particles, and in the rest frame of the particle determine how long it lived before decaying and how far it moved before decaying. Okay. Right. So this is problem 14. Now I will go a little bit formal about this problem. I'm just going to draw two reference frames. So one is I'm going to call S, the other one is going to be S prime, and S prime is going to be moving at some velocity with respect to S in the positive x direction. Right, so X, Y, and Z, X prime, Y prime, and Z prime. Right, so this is going to be our lab frame, and this is going to be our particles frame. So you don't need to be this formal about this problem. I just want to make this general so you can actually look at and solve more complicated problems. So they're telling us that this particle is moved 1 meters in a certain amount of time. Let me just check what that time is. 3.40 nanoseconds. So these are all measured in the lab frame. So delta x is equal to 1 meters, and delta t is going to be equal to 3.40 times 10 to minus 9 seconds. And they're asking us in the particle's reference frame what's delta x prime and what is delta t prime. Okay. So what is this velocity v? Well, in the reference frame, in the lab reference frame, that this frame, the particle, is going to move 1 meter in so much seconds, so its velocity is just going to be or the speed is just going to be 1 divided by 340 times 10 to the 9 meters per second. Okay, so this is going to be the measured speed of the particle, or the reference frame of the particle. Now, so from particle's point of view, the creation of the particle and the annihilation or decaying of the particle takes place at the same location. So we are going to have in the particle's reference frame these two events, the creation of the particle and its disappearance. They take place at the same location, right? Obviously, the particle is at rest with respect to itself. So in this reference frame, the particle is always at rest. Its location does not change. And because the creation and the annihilation takes place at the same location, the particle's location, the two events take place at the same coordinates, which means that one of the observers, the observer in the S prime reference frame, is actually measuring the proper time. Which means that to calculate this delta t prime, we can use time dilation. So this is going to be the dilated time with respect to delta t prime. Delta t prime is going to be the proper time. Right, so this is proper time. And conversely, when we're measuring the length that this particle has traveled, presumably in the lab frame, we just took a ruler, which was at rest with respect to the lab, and this was just like, and we measured the distance between two events taking place. And so this will be the proper length of that ruler. Whereas with respect to this particle that's moving at some speed with respect to the lab and also with respect to the ruler is going to be contracted. Right? So this will be the proper length. Now, because one of the length measurements is proper length, we can actually use length contraction, and because one of the time measurements is proper time, we can actually use time dilation formulas. Right? So this is very important, that you have to actually verify that you can do this. So if neither of the observers is measuring proper time, you can't use time dilation. You have to use the Lorentz transformation formulas. And likewise, if none of the observers are actually measuring the proper length of an object, you can't use length contraction formulas. But in this case, they are fine. And so for both of them, we are actually going to multiply or divide by the same factor. Right? So this is the factor by which we are going to divide or multiply. And so what kind of number is this? So v square by c square is a number between 0 and 1. We subtract this off from 1. We still get a number between 0 and 1. We take its square root. We get a number between 0 and 1. So if I multiply by this number, I get a number I make the number smaller. If I divide by this number, I make the number larger. Right? So this is the proper time. So it's the shortest shortest time that's observed. Everybody else is going to see some dilated time, some longer time. So this delta t is going to be larger than delta t prime, and this is the proper length. So this is the longest length that we are going to have. Everybody else is going to measure some shorter length. So we are going to have our delta x is also larger than delta x prime. Okay, so which means that is this correct? So the particle is going to take a very short time in their own reference frame. It's going to be dilated to a longer time in the lab frame. Yes, the particle is going to travel a long distance in the lab frame, whereas they are going to see some short distance. Yeah. So this does check out. So if you cannot make the full reasoning, you can just think of the muon experiment that I referred to and come to these conclusions. Now, once you come to these conclusions, with the additional fact that you can actually use time dilation and length contraction formulas, this is very easy to write. So this vector is going to be so delta x prime. I want this to be smaller than our delta x, so it's going to be just this 1 minus v squared by c squared times delta x, and delta t prime is also going to be smaller, minus v squared by c squared times delta t. Okay. And I'm not going to carry out the calculations for this, but yeah, there could be some tricks in carrying out those calculations, and we are going to look at those tricks in the next problem, which they're actually explicitly asking you to carry out those tricks. So the next problem is problem 69. So we have an atomic clock that's taken to the North Pole while another stays at the equator. How far will they be out of synchronization after 2 years have elapsed? And they are giving you the hint to use the binomial expansion. Okay. So why would one of the clocks be delayed? Why would there be some time dilation that's taking place for one of the clocks? With respect to the clock at the North Pole, the one at the equator is going to be moving because of the rotation of Earth, right? So in fact, we can actually calculate its velocity, calculate its speed. So this is 69. So we have two clocks. One is moving with respect to the other, and so one is going to experience time dilation. Now there is no Stevens paradox here. One is in an accelerated reference frame. One is continuously changing their reference frame. So the clock that's at the equator is going to be delayed, right? Less time is going to elapse for that clock, so it's going to be a little bit behind the other clock. So what's the velocity of that clock? Well, that will be the circumference of Earth divided by 24 hours. Right, so the circumference of Earth is 40,000 kilometers divided by 24 times 60 times 60. So this is meters per second. Right. So can we simplify this a little bit? I guess so. Yeah, so this is 6. This is 2 to 10 to 5. So 10 to 5 divided by 6 cubed. A little bit funny, but it's fine. Is that correct? I think so, yeah. So V over C is going to be 10 to the 5 divided by 6 cubed by 300,000 kilometers per second. So you need to carry this out. I think I made this calculation already to get some number, something like 1.5. Yeah, 1.5432 times 10 to minus 6. Okay. So this is a very small number, and again, so one of the clocks is going to measure 2 years. The other one is going to measure some 2 years multiplied by this factor that we just calculated. So one is going to measure 2 years. The other is going to be 2 years times 1 minus v squared by c squared. Right, so this is a number that's less than 1. So one is going to measure something slightly less than 1. And they're asking us to use the binomial expansion. So this is a small number. Its square small with respect to 1, its square is going to be even smaller. So did I calculate the square as well? Yes, I did. So v square by c square is going to be equal to 2.38 15 times 10 to minus 12. So this looks like 1 plus a small number raised to some power. And we are going to use the binomial expansion, which is just telling you 1 plus x to n is approximately equal to 1 plus nx for absolute value of x being much smaller than 1. Right, and it certainly fits the bill. This is the absolute value of that is certainly much less than 1. So this is going to be approximately 2 years 1 minus a half v square by c square. So we can just take this. So this difference is going to be just 2 cancels a half. Difference is just going to be this much times 1 year. So that's gonna be delta t is going to be 238 times 10 to minus 12 times 315 times 10 to 7, which is the number of seconds in a year. Did I calculate this as well? Yes, I did. It comes to something like 7.5 times 10 to minus 5 seconds, right? Or 75 microseconds. So this is something definitely measurable using atomic clocks or using some averaging over more ordinary clocks. Okay? So this binomial expansion is something you're going to do again and again. So in this case, this factor was in numerator. So 1 plus, let me just raise this. So this 1 minus v square by c square to a half is just becomes 1 minus v square by 2 square. It could also be in denominator. So in that case, we would have 1 minus v square by c square to minus a half, and then what you get into the front is minus a half, right? This just comes to the front still, and we're going to have 1 plus v square by 2c square. All right. So this is a number that's slightly less than 1. So if you take its square root, you end up with a number that's slightly less than 1, which is what you would expect. This is a number that's the reciprocal of a number that's slightly less than 1, so it's a number that's slightly larger than 1. And this right-hand side is also a number that's slightly larger than 1, so that also checks out. So this is a basic application of both the time dilation formula and also the binomial expansion in relativity setting.